Welcome back. In this lecture, I will talk about linear step polymerization and continue the discussion on molecular weight control and talk about molecular weight distribution and polymerization kinetics of linear step polymerization. Now, in last lecture, we discussed how we can control the molecular weight with conversion or how degree of polymerization is related to conversion, and we started with a simple system where either we have taken a AB type monomer where the molar ratio of two functional groups are always 1:1, or we have taken two monomers where AA type or BB type, and we have taken this in equimolar mixture. Now, in that case we have found that degree of polymerization is related to the conversion by this equation, and we call that equation as Carothers equation. Now, we also said that controlling polymer molecular weight by this controlling conversion is not recommended, because at the end of polymerization if we do not control in other way, then we are always left with the functional group present at the end of polymer chain, which can further react with themselves. So, that during processing we might get a instability in molecular weights. Next, we discussed how we can control the molecular weight by controlling the stoichiometry of the functional group, and we have taken AA and BB type monomer, and we have shown that degree of polymerization is related to conversion and R, which is the ratio of the functional groups, so that it is always less than equals to 1. R is given by Na by Nb if Nb is greater than the amount of Nb, a number of functional group of B is greater than Na. So, Na is number of functional group A and Nb is the number of functional group of B. Now, if Na is having higher number than Nb, then R we should define as Nb by Na. And in this case, if we can manage to push the reaction till completion or towards p equals to 1, then this expression will become 1 plus R divided by 1 minus R, or if R is 1, we get the Carothers equation, which we talked in last slide. Now, there is another way we can control the molecular weight. We discussed that by addition of chain stopper, and we have discussed that this is the expression where we have considered two monomers in equal ratio, AB type monomer or equal mixture of AA and BB type monomer, but in that case R is defined little differently, where Na by Nb plus 2 Nb prime, where Nb prime Nb prime is the number of B molecules present, which are monofunctional. These two is basically due to the fact that one single monofunctional monomer actually do similar effect like excess of one difunctional monomer. So, if we see this graph, how to control the molecular by stoichiometric control, we can see this graph where this is the excess of one of the monomers, say for example, in this case BB. So, the R value correspond to this would be 100 by 101, this would be 100 by 102, 100 by 103, this should be 100 by 104, and this is XS is 0, that means R is 1 in this case, in this point. Now, if we are plotting Xn, degree of polymerization in y axis, and let me write these numbers. And these are for different value of p. So, this is p equals to 1, this is p equals to 0.995, p equals to 0.990, p equals to 98, and this is p equals to 97. So, basically this is the direction where we are increasing p. So, from this you can see that degree of polymerization dependent on both ratio and the conversion. Now, if you want to achieve high molecular weight or high degree of polymerization maybe in this region, then you need to do reaction such a way that P should be very high and R should be as close to 1 as possible. If you are far away from, if you are basically imbalance increases or R is away from 1 or P is less, then you are bound to get lower and lower value of degree of polymerization. Let us give an example. We talk about say polyamide from the reaction of adipic acid and hexamethylene diamine, and we have 3 scenarios in this case. First is molar ratio is 1:1 and P is 0.995. Second scenario where we have one of the monomers say adipic acid present in 1% excess and having same P 0.995, and third case where we have same thing molar ratio 1:1 and P is equal to 0.995, but we have added benzoic acid which is a monofunctional molecule which has present as 1% extra, 1% excess with respect to the monomers like adipic acid. Now, so first case P is 995 and molar ratio is 1:1. So, we apply this formula Carothers equation to get Xn is equal to 200. In second case P is 0.95 and R is 1% excess monomer. So, 100 by 101. So, we put this number here and we get Xn is 100.5, and in third case P is again 995, R is 100 by 100 plus 2 into that 1% excess which we have, which will turn out to be Xn, value of Xn is 67.3. Now, you can see that just adding 1% monofunctional reactants which are basically chain stoppers, they have, it has more effect than adding 1% excess of one of the monomers. So, that is why it is very important that your reaction mixture should be devoid of any monofunctional monomers present in the system. And if you want to reduce or if you want to control the molecular weight, you can always use this monofunctional monomer as a chain stopper to reduce the molecular weight. Just to say how you get the molecular weight, just we have seen that Mn is Xn multiplied by 130, repeat unit for this polymer is 226. So, the molecular weight Mn would be Xn multiplied by 113. Next, we will go to statistical theory of molecular weight distribution in linear polymerization, and we will talk about size distribution, and we will again consider the simplest situation where we have AB type monomer or equal ratio of AA and BB, and this distribution is provided by most probable distribution is provided by P.J. Flory. Now, I am not deriving this expression, this is the final expression where Nx is the number of molecules of degree of polymerization of a particular value at conversion P, where An is the total number of molecules present at conversion P. So, Nx is the number of molecules of degree of polymerization value of x. So, basically this is equivalent to x mar. So, Nx is the number of molecules of x mar. Similarly, with N naught, then we get this expression where N naught is the initial number of molecule and N is the total number of molecule present at that particular conversion P, and W is the weight fraction of the x mar and rest of the, and x is the value of x mar. So, if you are talking about dimer, then x is 2, if you are talking about octamer, x is 8 and so on. So, this expression can be used to calculate in a reaction mixture what is the mole fraction of a particular mar or weight fraction of a particular mar. For example, we can calculate this monomer percentage for an equilibrium step growth polymerization 99%, what is the fraction of by mole percent and weight percent. So, this is the formula we should apply for mole fraction, and so mole fraction would be your mole fraction Ni or Nx. This is the mole fraction of x mar, which is given by Nx by N. So, 1 minus P to the power, x is 1. So, 1 is to 1. So, basically P is here 99%. So, 1 minus 0.99, this is 1. So, is equal to 0.01. So, basically the mole fraction of, in this case we are talking about monomer, x is equal to 1, we are talking about monomer. So, x is equal to 1. So, monomer mole fraction is 0.01 or 1%, which means even after 99% conversion, we still have 1% of the molecules present as monomers. Whereas, if you want to get the value for weight fraction, we should apply this expression, and in this case x is 1. So, 1 minus 0.99 square P 1 minus 1, which will turn out to be 0.01, 0.0001. So, the weight fraction of the monomer is much lower, which is basically 0.01 percentage, which means by weight in the reaction mixture the monomer has about 0.01% in the reaction mixture. So, by number, when you find a distribution, as we probably seen, again we will see now that the lower molecular weights or lower mass are present more in number than in weight. So, this is the mole fraction of so, this is the mole fraction of x mar. So, this is the x mar. So, 50 means 50 degree of polymerization, and these are for different p value. So, this is p is equal to 0.095 and this one is for 98 and this is for 99. So, as you can see that with when you have lower conversion or lower amount of reaction, then percentage of low molecular weight in terms of number percentage is much higher. As reaction goes towards completion or more and more reaction happen, the monomer percentage or the low molecular percentage goes down, but still even at 99% conversion, you can see that the percentage of lower Mars have much higher in number. So, in case of number, the if you have a lower Mar, will be always, it will present always in higher number than a Mar with higher x value. So, which means in any condition I will have more number of tetramer present in a reaction mixture compared to say pentamer, and that will always happen. Obviously, the difference will come down as we increase the p value or we proceed towards more completion towards the reaction. Now, this will be little different when we talk about weight fraction of this x Mar. In that case, this is p is equal to 0.9, this is p is equal to 0.95, this p is equal to 0.98 and this is p is equal to 0.99. So, in this case, as you can see, is always the Mars which have intermediate value, they have the highest weight fraction, and this goes towards more this peak where the weight fraction is having the highest weight fraction. The Mars which will which are having highest weight fraction, this shifted towards right or higher x value as we increase the conversion or as we go towards completion of the polymerization reaction. So, there is little difference, as you can understand that there is little difference between number fraction distribution as well as weight fraction distribution in a step growth polymerization. So, when you take this is for simple 1:1 molar ratio. So, we have x n given by this value and x w, which is the weight average degree of polymerization, is given by this value. So, the dispersity value or polydispersity index always given by 1 plus p. Now, so this is the derived dispersity value for a step growth polymers. Now, for a you can understand that for a high molecular weight step polymer, p value would be close to 1. So, the dispersity value should be always close to 2. Now, in practice actually we get little above 2, and that happens because of two reasons. One, when you isolate these polymers say by precipitation mechanism or some other method, then some of these low molecular weights are stripped off from the polymer mixture. As a result, the x w goes up, and also x w goes up comparatively higher than x n, and also there is always a probability of forming cyclic molecule, and once this cyclic molecule forms, then this dispersity goes little above 2. So, like 2.2, 2.3 and so on, but we cannot avoid completely the cyclic formation, but we can minimize by carrying out the reaction at higher monomer concentration and so on, which I am not discussing in this lecture, this introductory course. but there are ways to minimize the formation of cyclic. So, what from this slide, what you should remember that this is the number distribution, what it looks like, and this is the weight distribution, weight fraction distribution, how does it look like. And for a step polymer, for a high molecular weight step polymer, the dispersivity value is always near 2, but in practice we get little above 2. We will now move to the next topic of kinetics of step polymers. Now, we will go back and just look at the mechanism once again, how the step growth polymers are formed. There are many reactions possible in a reaction mixture, and what we need to, if we need to calculate the rate expression for each individual reaction, that it's almost impossible to do the reaction kinetics for the polymerization reaction. So, for this there are few assumptions. Assumptions are that reactivity of both functional groups of a bifunctional monomer are same. So, if I talking about a AB type monomer, then the reactivities of A functional group and B functional groups are same. And next, the reactivity of one functional group of a bifunctional reactant is same irrespective of whether the other functional group has reacted or not, which means that if this B has reacted, it has not reacted, the reactivity of A does not change. And the third is that the reactivity of a functional group is independent of the size of the molecules to which this is attached, which means that if I have a dimer or a trimer, or I have a tetramer or even hexamer or pentamer, the functional group which is at the end, say like if you are talking about the polyesterification, the acid group at the end of either of these mers have same reactivity irrespective of the size of the molecule to which it is attached, which means effectively the reaction kinetics of each of these reactions are same, and we basically call this principle as equal reactivity of functional groups. And this is not just assumption, these assumptions are established experimentally. So, which means these are a fair assumption. So, it is not that we are assuming something to make our life easy, but this is experimentally proven that these are indeed the case. So, if we assume all these things, then we can just write this as a general reaction of N mer plus M mer giving N plus M mer. So, we can just write the reaction like N mer plus M mer, N plus M mer, and if we talk about the reaction between functional group A and B. Now, most cases the step polymerization are performed in presence of catalyst. So, we write catalyst and we get this reaction, this is general reaction plus catalyst. Now, in this particular case we are assuming three things, or we are considering three things, that the low molecular weight condensate like say polyesterification, water or some HCl or whatever is coming out during this reaction, we are removing completely. So, basically this reaction is a irreversible reaction. So, we are only putting the forward direction. So, we are talking about irreversible polymerization, and AB monomer type, in the simplest case where we are talking about only AB monomer type or equimolar mixture of AB and BB. So, we can we know the rate of polymerization or rate of reaction is the rate of disappearance of a functional group. So, in this case, because we can consider either A or B, both are same. So, we can write rate constant, concentration of A and concentration of B and concentration of catalyst, and catalyst concentration is constant. So, we put this within this new rate constant, giving A plus B. Now, we know that the equimolar stoichiometry we have considered here. So, concentration of A and B we consider as a C. So, we write the rate expression like this, and we do this integration where C 0 is the initial at t is equal to 0, C is C 0. So, initial monomer concentration. So, we just do some rearrangement where P is the basically conversion, the fraction of functional groups which reacted at time t. So, we get this expression. So, eventually we get xn degree of polymerization is given by 1 plus C naught k T, where C naught is the initial monomer concentration. So, this is experimentally verified, where this is x n, or which is equals to 1 by 1 minus p, that what we got, and this is time in minute, and this is verified for a reaction between adipic acid plus ethylene glycol catalyst by PTS, pan-toluene sulfonic acid, at a temperature of 109 degrees centigrade. So, whatever we have derived from that rate equation is experimentally verified. I have given you one example in this particular case. Now, there could be another possibility where we are not adding any external catalyst. Oh, okay, this is example we just wanted to show you, and so basically this shows we need to show that the time required to go from P 0.98 to 0.99 is very close to the time to reach from 0.98 start of the polymerization. So, if we quickly try to show this, that we know this expression C naught k T is equal to 1 by 1 minus P minus 1. So, T is given by P k C 0 1 minus P. Now, when P is 0.98, we write T at 0.98 divided by K C 0 1 minus 0.98 98, which gives us 49 by K C 0. Similarly, we can find out for P 99, which will give us T of 99 by K C 0. So, the time required to go from 0 conversion to 98 conversion is given by this value, and the time from 0.98 to 0.99 is given by difference between this number and this number, which is 50 by K C 0. So, this is the time for this, and this is the time for 0 to T 0.98, which means for completing the reaction up to 98% is almost took us same time from going from 98% conversion to 99% conversion, and that happens because when we are have converted 99%, that means 99% functional groups has reacted. Now, the effective concentration of functional groups are very low. That is the reason why the reaction rate, which is reaction is a bimolecular reaction, is a reaction between two functional groups, because the functional groups concentration has reduced drastically, that is why the reaction rate comes down. So, which means basically for a step polymerization we can achieve the some value of conversion very fast, but to get a very high value of conversion we need to run our reaction for a much longer time, because that it is very difficult to build or achieve the high conversion at later part. So, with this I will stop for this lecture, and next lecture I will start with another possibility of step polymerization, which is not very practically done. This is externally catalyzed polymerization is the most frequently done step polymerization, but I for a completion of record I will start with another possibility of step polymerization, kinetics of step polymerization, where we will not add any catalyst from outside. One of the reactants can actually be used for a catalyst. So, that we will start in next lecture.